Good afternoon, everyone. I am Mizi Terence Esparan, and today, together with my co-reporter, Raisa Montemayor, we will be exploring about Scipy, which is a powerful Python library for scientific and technical computing. So our presentation will cover its various sub-packages, their functionalities, and how they can be applied in different scenarios. So our objectives for today's presentation includes introducing you to Scipy and its capabilities. Second is discussing the different sub-packages or the modules within Scipy. And then the third one is to understanding the various functions available in each module. So Scipy, in short, which stands for Scientific Python, so it is a free and open source library widely used for scientific and technical computing. So it is a collection of mathematical algorithms organized into sub-modules or what we call the sub-packages tailored to address various scientific needs. So the development of Scipy was motivated by the need for an open source library capable of handling complex mathematical computations across different specific domains. So it was created in year 2001 by Travis Oliphant, Peterson, and Eric Jones. So they aim to enhance Python capabilities for scientific computing. So Scipy offers a wide range of functionalities, including advanced linear algebra functions like matrix decomposition. Second is an extensive collection of statistical functions for data analysis. And then the third one is basic image manipulation tools for image processing, such as rotation. Ganun. So the fourth one is numerous special functions crucial in many scientific applications. So Scipy is organized into several modules, including scipy.linalg, scipy.stats for statistical analysis, scipy.indimage for image processing, and scipy.io for data input and output. So the scipy.linalgebra module is short word for linear algebra. So it provides a comprehensive set of functions for various linear algebra operations. So it is widely used across different subjects, offering fast linear algebra capabilities, according to Candido 2024. So here are some examples of functions available in scipy.linalg. So we have linalg.solve, which solves linear equation, and then linalg.det, which calculates the determinant of a matrix. So the third one is we have the linalg.eig, which computes the eigenvalues and eigenvectors and so on. So later on, we were going to illustrate these functions in a software. And here are more examples of functions in scipy.linalgebra. So we have linalgebra.expm, which computes the matrix exponential. And then we have also the linalgebra.logm, which computes the matrix logarithm, and also the LU decomposition. So now we will proceed to the scipy.ndimage, which provides functions for multidimensional image processing or n-dimensional array. So it includes various operations like filters, transformations, and measurements on n-dimensional arrays. So this Scipy provides the ndimage package that contains the number of general image processing and analysis functions. So some of the common tasks in image processing, such as basic manipulations or of image, such as rotating the image, like so on and so forth. So here are some examples of functions in scipy.ndimage. So we have here ndimage.rotate, which rotates an image, and then ndimage.filters, that Gaussian filter. So this function applies a Gaussian filter to an image, and then the last one is the median, which applies the median filter to an image. So this time, we will illustrate some of these functions in action using Thonny and Jupyter Notebook. So let us first illustrate the first sub-package of Scipy, which is scipy.linear algebra. So first, number one is solving a system of linear equations. So we have here an array, two array, A and B. So this part solves a system of linear equations in the form of this one. So The matrix A represents the coefficients of the variables, while B represents the right-hand side values, or what we call the constants. So the function linalg that solve A, B is used to find the solution vector x, which will contain the values for x, y, and z. So we have here the resulting value. So we have here x is equal to 2, y is -1, and z is equal to 1. Second is getting determinant of a matrix. So the determinant of a matrix tells us certain properties about the matrix, such as if it's invertible or not invertible. So if the determinant is 0, then it is invertible. So here, the matrix A is passed to the linalg.det function, which computes the determinant. The result is printed out, which is 3.99. So since hindi siya 0, it means that the matrix A is invertible. Now we proceed to the eigenvalues and eigenvectors. So eigenvalues and eigenvectors are properties of a matrix that can be useful in areas like physics and machine learning. So in this, we have to use square matrix. So in solving for the eigenvalues and the eigenvectors, the matrix used should be a square matrix. So the linalg.eij function computes both the eigenvalues and the corresponding eigenvectors of matrix A. So now we proceed to trigonometric functions on matrices. So trigonometric functions like the sine, cosine, and tangent and can also be applied to matrices, not just scalars. So these functions compute the sine, cosine, and tangent of a matrix respectively. So the matrix A is created as a 3x3 matrix, and then the trigonometric functions are applied to it. So we have here the result. Then we have the hyperbolic trigonometric functions for matrices. So this section applies hyperbolic trigonometric functions sine hm, cosine hm, tan hm to a matrix A. So these functions are analogous to the standard trigonometric functions but for hyperbolic functions. Now let's proceed to computing matrix exponential. So the matrix exponential exp of A is a function that can be applied to a square matrix. So it is generalization of exponential function. So the function linalg.expm of A computes this matrix exponential of the matrix na A. Then the seventh one is computing matrix logarithm. So similar to matrix exponential, matrix logarithm is the inverse operation. So it is the matrix that when we exponentiated, it gives the matrix A. So the function linalg.log m of A computes this logarithm. So we have here the result. And then the eighth one is the LU decomposition. LU decomposition factors a matrix A into the product of a lower triangular matrix and the upper triangular matrix U. So while QR decomposition naman here in 9 is the product of an orthogonal matrix Q and an upper triangular matrix R. So this composition is widely used in numerical methods for solving linear systems and eigenvalue problems. So this code here is given din to sa website na na-search ko. Then we have last is the singular value decomposition. So we have here the factors of a matrix A into 3 matrices, which is U, then the sigma, and then the V raised to T. So U stands for left singular vectors. Sigma is diagonal matrix. So this decomposition is widely used in signal processing. So data compression and dimensionality reduction techniques like principal component analysis. So this code here is na-search ko lang and may i-add ako na ang SVD pala is like sabi ko kanina na ang eigenvalue at eigenvector is applicable siya sa square matrices. While ang singular value decomposition naman, applicable siya sa square matrices, pero most used po siya sa non-squared matrices. Non-squared matrices, example, 2 by 3 or 3 by 2. So, each section demonstrates a different aspect of matrix computation, primarily using the Scipy.linalg library to perform advanced matrix operations commonly used in linear algebra and scientific computing. And now we will proceed to using the Scipy.ndimage library using Jupyter Notebook. So this code demonstrates how to apply various image filtering techniques to an image using Scipy ndimage and Matplotlib libraries, and then visualize the results. So Scipy.ndimage, as we all know, this contains a collection of image processing functions such as filters and transformations to manipulate the image data. And then Scipy.misc, so this module contains utility functions for working with images. So I use here mic.face, which loads an example of an image. And then the matplotlib.pyplot is used for creating visualizations such as plotting images. So the MISC face loads a default sample image of a raccoon face. So this one, in this line, we apply the Gaussian filter, which smooths the image, reducing noise and detail. So the sigma parameter controls the spread of the filter. So larger values results in stronger blurring of the image. So here we use the sigma equals to 3, means the image will be blurred with a standard deviation of 3. And also we add the median filter, which used also to remove noise, particularly salt and pepper noise. So each pixel is replaced by median value of its neighbors. So a 3 by 3 window here as specified by size 3. So also, Sobel filter is a type of edge detection filter that emphasizes the edge of an image by calculating the gradient of intensity at each pixel. So basically, these are all filters applied to a single image. And then we have the Laplace filter, which highlights areas where intensity changes rapidly, which are typically the edges. And then last one, we have the Prewitt filter, another edge detection filter similarly to Sobel, but also computes gradients, but it uses a slightly different kernel to highlight edges. And then plotting the results. So we have here 3 number of rows and 2 number of columns. The grid will be a 3 by 2, creating a space to plot the image in a 3 by 2 grid format. So the fig size 8 makes the figure 8 inches by 8 inches in size. Then we display the images. So plt.show, so this function displays the entire plot with the subplots of the original image and all the filtered images. So we have the top left here, the original image, which is the raccoon face, and then the image after applying the Gaussian filter, blurry effect. Then middle is the image after applying the median noise, the median filter, noise reduction. And then at the bottom right, we have here the image after applying the Laplace filter, detects areas of rapid intensity change. So basically, each subplot will have its corresponding title. The second one is demonstrates how to rotate an image using Scipy.ndimage. So we use the Scipy.ndimage and then the Scipy.misc. And then we have here misc.ascent. So this function loads a built-in test image. So kanina is face yung raccoon na face. Ngayon naman is the ASCENT. So it is a small 2D image of camera view. So rotating the image, so we use the Scipy.ndimage interpolation rotate. So this function rotates the input image by the specified angle we set, which is 180. So the rotate function performs the rotation by performing the image pixels position. So we have here again angle equals to 180, which rotates the image 180 degrees, flipping it upside down. So the result stored in a rotated image. Then we have setting up subplots. So we have here we create a figure of layout of 1 row and 2 columns. First first column is the original image, and then the rotated image. So again, so in output, the second one displays the rotated image. So in the second subplot, which is in the right side, by the use of PLT tight layout and the PLT.show, we were able to display the figure with the two subplots, the original and the rotated image, so side by side. So that's all for my part, and I will now give the floor to Ms. Raisa Montemayor for the part 2 of this video lecture.